Okay, it is my pleasure to introduce Maggie Brucker, who is giving her Ph.D. defense seminar today. Maggie began her career at UW-Madison as a Sims graduate student in September of 2017. I was her, at that time, her co-advisor with Steve Ackerman. I became her academic advisor in 2019, and she completed her MS in 2020, where she was using the RAQMS aura reanalysis, which you'll hear about some today, to do indirect validation of satellite stratospheric ozone retrievals. She was awarded the Latau Award in 2021 for Best MS Thesis for that work. She was also awarded the William M. Lipenta internship in June through August of 2021, where first of all she did it remotely because of COVID, but even doing this remotely, she became an active member of the Melodies Monet Model Verification Development Team and continues to participate in that. I'm not going to tell you what the acronym Melodies Monet means because it's long, but basically it's bringing verification tools that are used for operational weather forecasting to add chemistry capability to that. She's been in the field as part of our chemical forecasting and flight planning team during the 2019 FireXAQ field campaign, and her PhD work uses that campaign data extensively. She was also part of the 2023 SABRE and 2023 Aroma Stacks Ages field campaign. All in 1 year, she went from forecasting the polar vortex out of Fairbanks, Alaska, to predicting urban megacity chemistry and telling the DC-8 which city they should fly in the summer of 2023. That summer of 2023 was when we did the first air quality field campaign under the new TEMPO satellite, which is a new geostationary atmospheric composition satellite. She's an avid downhill skier. She loves backpacking. Did a trip on the Wisconsin Ice Age Trail that I think she encountered lots of swamps and lots of bugs. And she's an ultimate Frisbee player. So today she's going to present her PhD research entitled Impact of Tropical and Boreal Biomass Burning on Atmospheric Composition. Maggie is also my first PhD student, so welcome, Maggie.
All right, thank you, Brad. All right, so let's dive in. So biomass burning has a significant impact on air quality globally. Fires like the Park Fire currently burning in California and the Canadian fires of last summer and this summer present a major source of trace gases and aerosols to the atmosphere. And these are also ozone precursors, and so we later have to deal with ozone formation from them as well. They present a significant health risk, both in the short term, where it can impact people's respiratory breathing, and then later on, where it can contribute to premature deaths. The burn scars left behind by wildfires significantly change the landscape, and a secondary hazard is the debris flows, and then the long-term changes in landscape as the vegetation reestablishes. Biomass burning emissions peak twice during the year. First, a small peak in February through March that's primarily emissions from Southeast Asia. And then the secondary peak when a large number of regions are burning, like the Southern Hemisphere, Africa, Equatorial Asia, the Boreal, Siberia, and South America. So we use chemical transport models to predict the chemical evolution and physical transport of emitted pollutants. Here is an example of a HER smoke forecast from NOAA a few days ago, where you can see the Park Fire from California and then other fires burning along the West Coast, the transport of the smoke across the United States. and outside of the domain. So some guiding questions of my research are, how is variability in tropical tropospheric ozone related to biomass burning emissions? How well do global models capture these emissions from biomass burning? And then, what is the contribution of the biomass burning emissions to the global background air quality? So to do this, I use a couple of modeling systems that I'll describe briefly. The first is the real-time air quality modeling system, or Re-analysis, that covers 2006 to 2016, run in replay mode, where the chemical forecasts are constrained with observations from satellites. This is a global scale model that is run at 1 degree resolution, and the biomass burning emissions are calculated using a severity-based burned area approach. So the second portion model that I'll be using is the UFS-RAQMS, which is an updated version of RAQMS, where the chemistry module has been coupled to NOAA's operational unified forecast system instead of the UW hybrid model. And the biomass burning emissions are from the blended global biomass burning emissions product, or GBPX. And we've increased the resolution to 0.5 degree. And the simulations that I use in this experiment, or in this dissertation, are of July through September of 2019, an example forecast of which is shown here, and it's run in replay mode again. So to go to my first question, how variability in tropical tropospheric ozone is related to biomass burning emissions, I evaluate the impact of the El Niño-Southern Oscillation on tropical tropospheric ozone variability in the UFS-RAQMS model, or reanalysis. I look at use ENSO composites of the horizontal structure. And look at use these then to look at the vertical structure as well, and compare to observational data sets, the tropical rainfall measuring mission, monthly precipitation, the total column CO from the Moffett instrument, and then tropospheric ozone columns, residuals from the OMI and microwave load sounder. So here I've got a schematic of the impact or the influence of ENSO on tropospheric ozone. The El Nino, in response to the warming SSTs in the Central Pacific, the Walker circulation shifts to the core of the Walker circulation, and updraft shifts to the Central Pacific, which this increased convection over the Central Pacific lofts the low ozone air masses from near the surface over the Pacific aloft, and then with the descending motion over the maritime continent, the high ozone in the upper troposphere descends. And alongside this, the decreased precipitation over the maritime continent leads to a drier environment and increased biomass burning and emissions from this. And then we have increased ozone production. The La Nina is largely opposite of this, and it should be noted that the wetter maritime continent, we have fewer biomass burning events and decreased emissions. So looking first at the El Nino precipitation composite, here we've got the RAQMS, or Re-analyses precipitation, and then in the center, the trim precipitation, and both capture a very similar thing with the enhanced precipitation over the Central Pacific and decreased precipitation over the maritime continent. We then can look at the vertical structure of this response with the convective max flux from the model, and have enhanced upward flux over the Central Pacific and decreased upward flux over the maritime continent. So now that we've set the stage with the vertical or the convective circulations, look at the tropical tropospheric ozone column anomalies in the RAQMS ORA model and then OEMLS observations. We have enhanced ozone concentrations over the maritime continent and then decreased over the Central Pacific, which then moving to what this looks like in the vertical structure, the high ozone from the top, or from the upper troposphere, lower stratosphere is descending within the column. Then the low ozone from the troposphere is being wafted into the upper column. And then with this, we also have the suppressed convection over the maritime continent driving enhanced ozone production from the biomass burning emissions, which we look at using carbon monoxide, and which is shown here over the maritime continent, enhanced carbon monoxide in both the reanalysis and the observations. And then this is primarily within the lower troposphere over the maritime continent. So after looking at the vertical structure, we look at how this relates in time to the ozone using linear regression of the principal component time series that we get out of empirical orthogonal functional analysis applied to carbon monoxide precipitation and tropospheric ozone columns, trying to relate the biomass burning and circulation, how much of it contributes to the ozone pattern. In the interest of time, I'm not going to go through the entire composite analysis, or the entire UOF analysis, but the dominant modes of variability for precipitation and ozone are captured in principal component 1 and are highly correlated with the Niño 3.4 index, so we're fairly certain that this is our representation of ENSO. And the dominant modes and the principal component is for ozone is shown in blue on the top panel. And then the dominant modes of variability for carbon monoxide are captured in principal components 1, 2, and 3. The linear regression I built to quantify the contribution of the CO PCs and precipitation principal component to the ozone PC1. The reconstruction is shown in the orange on the top panel, and it reproduces things fairly well. And then in the bottom panel, the dark line is the contribution of the precipitation, which is the dominant factor, but the carbon monoxide in the red is contributing as well. But it's primarily driven by, for the ozone response to ENSO is primarily driven by precipitation and convection. So, in summary for this first question, the RAQMS ORA composites capture ENSO variability that's given in the observations, and the composites are consistent with our conceptual model of how ENSO impacts tropospheric ozone. And then the tropical tropospheric ozone ENSO variability can be reconstructed from the ENSO precipitation variability and our leading modes variability in CO columns. And the statistical representation shows that carbon monoxide column variability is associated with biomass burning. Associated with biomass burning does contribute to our total or tropospheric column ozone variability, but the predominant factor in this is the precipitation variability. So now we're going to move on to how well global models capture emissions from biomass burning. And as I stated before, we're now using the UFS-RAQMS model and looking at July 15th through September 30th of 2019. UFS-RAQMS uses the GBBX emissions. These are obtained using from satellite observations of fire radiative power, or FRP. And during this time period, the Siberian emissions were predominant at the beginning of the period, as shown in this blue, while later on, the tropical burning became the dominant source globally. And UFS-RAQMS trace gas emissions are obtained by applying the emission factors to the carbon monoxide emissions. So an uncertainty in the carbon monoxide emissions then cascades into the other ones as well. So I use CO column observations from the tropospheric monitoring instrument to assess the UFS-RAQMS control experiment and then conduct data assimilation experiments. And this is an example of a day of observations from the instrument. So starting with the UFS-RAQMS control experiment, looking at validating it, here we've got the average troposphere CO column on the left is the tropospheric column average for our time period from the instrument, and then on the right is the control experiment CO column. And you can see that we're underestimating the CO column over the Siberian biomass burning region, and the global background in the northern hemisphere is too low and slightly too high in the southern hemisphere. The boxes here denote the domains for the field campaigns that I'll be using, so CampX and FireXAQ. And then the red stars are the remote sensing profiles from the the Network for Detection of Atmospheric Composition Change that I'll be using in validation as well. So I assimilate tropospheric column data from troposphere into UFS-RAQMS using the grid-point statistical 3D variational data assimilation system. Here in this equation is the cost function that we minimize with GSI. It has two main components. The first part of the equation is the difference between the analysis and the forecast that is weighted with the model background error, and we get our background error for the model with the NMC method and have tuned it to be sensitive to forecast, or to the emissions, to the variability in the emissions. So then the second factor is weighted by the difference between the analysis and the observation. And the R matrix is from literature, and then the H is the observation operator is given by the troposphere average kernel. So the first results from our data assimilation experiment, here we've got the percent change across the simulation between the data assimilation experiment and the control, the change in CO column. And here we can see that we've increased the northern hemisphere CO and decreased the southern hemisphere CO. And then the largest increases are over our biomass burning regions in Siberia and the maritime continent. So now we validate our data assimilation experiment using independent observations here from the Moffett instrument, the CO columns, and here we've got the Moffett CO on the left, and then our data assimilation, or UFS-RAQMS troposphere data assimilation experiment CO on the right. And you can see that over the Siberian region, we have a good agreement between the CO concentrations, and have also a high background, or the background concentrations hemisphere are close as well, and then the southern hemisphere decreased. So how well did our global model capture the emissions from biomass burning? In the control case, it underestimated the global carbon monoxide concentrations, and then this was fixed by assimilating the tropomy observations, and particularly near biomass burning, but the tropomy CODA only compensates for uncertainties in the biomass burning CO emissions and doesn't actually adjust the emissions themselves, because we've set up our data assimilation to only adjust the column and not the emissions. And so this points to the need to improve the biomass burning emissions, which I will now discuss my attempts to do. So, as I discussed in the beginning, UFS-RAQMS applies emission factors for co-emitted NOx and volatile organic carbon species to the GPBX CO emissions, and so similar uncertainties to our CO are anticipated for these species as well, and this does contribute to potential errors in the ozone production within the biomass burning plumes. Inversion techniques are used to optimize the emissions based off of the observed atmospheric composition. So this is done in several different ways. One way is mass balance techniques, where a change in emissions is related to a change in concentration of whatever your observed variable is by way of a beta factor. And then other methods will directly adjust the emissions as part of the assimilation. So such methods include ensemble Kalman filters and adjuvants. So I use the iterative finite difference mass imbalance approach based off of work from East et al. And Lamsdahl et al. Here the first step in this is to obtain an estimate of the model sensitivity to changes in emissions. We get this by using first a simulation with the entire emissions, and then a perturbation experiment where we've decreased the emissions by 15%. And then we calculate the beta term given by the equation in the center that's boxed in blue. And then once we do this, we run an experiment using, or our next experiments will use the full emissions. And so we get run a regular experiment and then a data assimilation experiment, and use the analysis increments, or the CO analysis increments from the assimilation experiment to calculate with the finite difference equation given here our perturbed emissions. And then we, in order to get the best estimate that we can of our emissions, we run several cycles of the assimilation and calculation with the finite difference mass balance equation, and then determine that we have converged on our best estimate once the assimilation increments near zero and the change in emissions between the different iterations is near zero as well. So for our first iteration, we do get some fairly good changes, around like 200% for our largest regions, or for the regions where we've got the most biomass burning going on, but over much of the globe the change in emissions is fairly small. And then by the sixth iteration, which in this experiment we determined to be our stopping point because our assimilation increments were, or our analysis increments were small, and the change in emissions from the previous iteration was small, we get very large changes, greater than 800% over our Siberian and maritime continent regions, and strong improvements or strong increases over our other regions as well. So looking at some of these changes, first we have our change, or our emissions from the Siberian region, which the black curve is where we started, and then by the end, we've incrementally increased the emissions to where we've got a very strong enhancement in emissions. Over Africa, we'd see some change in magnitude as well, though not as much. And then over the from the Borneo region, we get a very large increase in emissions from our iterative adjustment process. So we next need to evaluate these adjusted biomass burning emissions. So because the iterative finite difference mass balance did significantly increase them, and so to evaluate them, I conduct a new experiment, or a new UFS-RAQMS control experiment that uses these new emissions. And so now we evaluate them, and I will be showing the results from each of the UFS-RAQMS experiments I've discussed. So the control experiment, the data assimilation experiment, and then the final adjusted emissions experiment. This top A panel is the difference between, or the percent change, or the percent difference between the control with the a priori emissions and the Moffett observations, where we have a low bias in the northern hemisphere and underestimate over our biomass burning regions in Siberia and maritime continent. The Tropomi data assimilation experiment here in the top right panel, we've largely reduced the background bias, though we have now a potential overestimate over the biomass burning. And then in this bottom is our new control experiment using posterior emissions, where we've largely reduced the northern hemisphere low bias, but there is still one pointing to other reasons for it, or pointing to additional reasons for that low bias's existence, like low anthropogenic emissions. And then we're now overestimating the tropical biomass burning. So I compare with the profile from our UFS-RAQMS experiments with the observations from the FIRE-XAQ field campaign that was occurring over North America, and looking at the smoke from North American fires. Here, the red is the UFS-RAQMS control experiment. The dark blue is the assimilation experiment. The black line is the observations, and then the light blue is the new emissions run. And you can see that over North America, there really isn't, during this period, there really wasn't that much difference between these, showing, which we would expect based on the fact that we've only got like a 10% change in our CO column on average. Over the Philippines, in the CampX, compared to the CampX observations, the colors are again the same. In the control experiment, we were largely underestimating the profile. In the DA case, we do get it fairly well. And then our adjusted emissions do get us part of the way to that improved profile. Looking at the high latitude Thule site, we can see that the assimilation does change the shape of the model profile, and for the most part, this does improve agreement with observations. But at the surface, we've increased the CO too much. And the adjusted emissions, we increase the concentration but don't necessarily change the shape of the profile. And then looking at another location, NDAC site, we have the tropomi, or the data assimilation profile. We've changed the shape again, but this time it's to the detriment and isn't capturing things, or isn't capturing the observed profile very well. And the adjusted emissions does keep the shape, but does not quite reach the what the observed profile should be. So now I can finish answering how well the global models capture biomass burning emissions. So the iterative finite difference mass balance using tropomi CO analysis increments increases the GBBX CO biomass burning emissions, and the resulting model simulations with this have an improved agreement with observations, and it did largely decrease, or the increased biomass burning emissions did largely reduce the northern hemisphere low bias during this time period. So now that we've got a better set of fire emissions, I look at what the contribution of biomass burning emissions to global background air quality is. I do this by looking at the difference between experiments using the posterior and prior GBBX emissions to look at the average atmospheric response. So here I have the zonal mean CO during the experiment, change in CO during our experiment between the run with the posterior and with the prior emissions, and then the change in the vertical column, and the CO increases globally, primarily in the lower troposphere. So ozone precursors are co-emitted with biomass burning aerosols and CO. And so since we've changed the emissions, we've also changed those. And I look here at the nitrogen dioxide, which the increases are very large and right near the biomass burning emission sources, and largely within the lower troposphere, and are of similar magnitude, or the comparative magnitude is alongside the CO. So regions with stronger CO changes, like the Siberian burning, have larger responses in NO, while the African region, where we didn't have a large impact in CO, we also don't have as large of an impact in NO2. So now we look at the resulting tropospheric ozone response, since those were the precursors to tropospheric ozone formation. And within the plume, tropospheric ozone increases, and we're looking at smaller percent changes than in our other compounds. And the increases in the tropics are stronger than the boreal regions due to the higher photolysis rate in the tropics than the boreal regions. So, to summarize this, and provide a bit of an answer to what the contribution of biomass burning to background air quality is, in UFS-RAQMS, the ozone precursors from biomass burning are dependent on CO emissions. And the strongest influence of the biomass burning emissions on CO, NOx, and ozone is right near the source. And the changes in the UFS-RAQMS NOx are right near the source are proportional to the change in CO emissions, while ozone production from biomass burning emissions is stronger in tropical biomass burning plumes than boreal biomass burning plumes due to that difference in the photolysis rates in the tropics and the boreal. So now we have the overall takeaways from my work. The variability in tropical tropospheric ozone is somewhat related to the biomass burning emissions variability, as the column CO variability associated with biomass burning variability statistically contributed to there was a statistical contribution, but the predominant factor was the precipitation variability. The global models capturing of biomass burning emissions in the simulations using the standard CO emissions, the observed CO distribution was underestimated, and then this was improved in the iterative finite difference mass balance approach and with using the tropospheric CO data assimilation. In answering what the contribution of biomass burning emissions to global background air quality is, I used the adjusted CO simulations to show that biomass burning emissions are a significant contributor to our global trace gas concentrations, and that the impact on ozone of these emissions is stronger in the tropical regions than the boreal regions. And again, this is due to the photolysis differences. So some next steps for this work are performing additional analysis on the UFS-RAQMS adjusted emissions experiment to kind of further look at what the impact of our changes in emissions were on chemistry within smoke plumes. And then I plan to analyze performance of UFS-RAQMS and GBDX CO emissions during a period that has stronger biomass burning in North America, because during our time period there really wasn't much burning going on in North America, and so we can't really get a good sense of how well the emissions were performing there. This will be done during my NRC postdoc with Brian McDonald and Becky Schwantes at NOAA Chemical Sciences Labs Atmospheric Composition and Modeling Group, where I will be looking into investigating the response of atmospheric composition forecasts to variability in the composition of biomass burning emissions. So, as anyone knows, you can't do this alone, and I have a number of people to thank. First, my advisor, Brad Pierce, who has given me more support than I think I could have ever wished for, and he's done so much for me. To my Ph.D. committee, Tracy Holloway, Matt Hitchman, Dan Beaumont, Jack Fishman, and Michael Morgan, who is no longer a member of the committee. Thank you so much for helping shape this research. Without your feedback, there would have been too many parts that were different from each other, and this would not be a cohesive whole. To Alan Lenzen, thank you so much for helping me with running UFS-RAQMS. To the entire AOS community, this has been a great place to be, and I'm so glad that I got to be part of it and be here. The intentionality that's put into building the community is wonderful. The members of my first year cohort and qualifying study group, I wouldn't have gotten through the first couple of years and all of the change that was going on in the department without y'all. To all of the members my office mates who've been with me in 1311, the SSC Sims grad student group. I didn't have a traditional research group, and you were great. All of the people that I met as part of the FireXAQ, SABRE, and Aegis Plus field campaigns, I grew a lot as a scientist during those times. My dissertation writing buddy, Rosa, I know you couldn't be here today, but it was great writing with you. You really helped keep me on track, and I hope to have been that for you. To all of the friends I've made in AOS over the years, playing broom ball, getting beers, just everything. It's been very fun, and you've helped keep me from getting too far into the weeds. The beer call group, yeah, thanks. I wouldn't have stayed sane in the pandemic without having y'all every week. My Frisbee friends, y'all helped get me through quite a bit. Frisbee was how I made sure I had something going on outside of research, and when I tore my ACL and couldn't play anymore, thank you so much for still letting me be a part of the group. And of course, to my family, all of the support you've given me over the years, it wouldn't have been doable. I thank you so much for all of the unconditional love and support, even though you might not understand anything I talked about. I love you so much. And now questions.
Thank you, Maggie. Very good timing, too. I'll take questions from the audience.
Great talk, Maggie. I was wondering if your emissions assimilation, if you compared it to any other emissions inventories that exist out there?
I haven't directly compared to any of them because we are working in a different time period than a lot of the other studies kind of looked at. But other work that's used or that has been adjusting emissions inventories gets fairly similar results. And the iterative finite difference mass balance method has been compared for other emissions adjustments to like the output from the adjoint, and they get very similar results, just with different computational modes.
Any other questions?
Hi, Matt. Great talk. So I know you said that the response to from wildfires on ozone is strongest near the source, right? Is that what you said?
Yeah, you get the strongest response.
So have you like quantified like how much it changes the background ozone, like overall? Like if you were to give it a value, like if we remove the wildfires, how much would global like ozone decrease?
Okay, so here for this period are in the background, like over here over the Pacific, we've got about a 4% change in tropospheric ozone, and so if we were to remove, we'd probably got a very similar response. So it'd be like a 4% decrease.
Any thoughts, Maggie, on what changes in summer Arctic cyclones in the northern hemisphere might have on ozone at high latitude at the end of the warm season? Because I couldn't help but see in your picture of the Siberian satellite movie,
Okay.
Or one,
Mhm.
it looked like that smoke was caught in a cyclone, much like the one you showed over us. So if
it
they
definitely does.
if there's more of them,
if your emissions get wrapped up.
yeah,
in that.
is there more of a flux of carbon monoxide poleward now than there used to be? Or is it tied to the frequency and intensity of Arctic cyclones?
We could potentially look at that within reanalyses. I don't have a good sense.
And then, does that
for-
provide a potential Band-Aid for ozone depletion in the northern hemisphere, cold season? I mean,
Are you looking in the?
I'm thinking about.
So here we're looking in the troposphere.
Right,
and
right.
there's less. There
Oh,
is
that's not
some
really the
flux
same
into
problem.
the
Yeah,
stratosphere.
yeah,
It's not really the same problem.
But nonetheless, is there an increase in ozone in the lower troposphere north of 65 degrees north or something? Has anybody noticed this?
I would have to get back to you.
Okay, yeah, I'm just curious because of what I saw in that picture, so,
Mhm.
okay.
There certainly is what you see is you see more black and organic carbon transport, and you can see that in, the record of additional black carbon on, ice packs.
Yeah, that can't be good for ice and snow, I believe. Yeah.
Great talk. My question's a little bit more like philosophical. I'm thinking, a lot of your metrics are looking at the percentage changes in emissions. If you were to swap over to absolute changes in your, whatever particulates you're looking at, do you see different spatial trends? And then that leads into a smaller question. I believe you were showing 3 different goal models compared to a control, and you had an anomaly within the Antarctic that wasn't captured well. I was wondering if that was due to errors within the goal models or through your control metric, and if that's just the result of using percent change, there's likely low amounts of carbon monoxide in the Antarctic. Is that?
Yeah.
So on this one, I did also do it in the standard column units for carbon monoxide, and the results are very similar. Are you talking about, could you remind me of the second part?
In the Antarctic, you see on the coastline, it's just high increases in terms of percent change. That it's consistent across all 3 models. I'm wondering if that's just due to there being little amounts of carbon monoxide in that region. Your control is just off in the Antarctic.
So there probably are some transport things going on, but here that is kind of during this time period, that is where we've got a lot of carbon monoxide that wasn't really captured in the in the control run.
Are you talking about the Arctic right now, the northern, or are you talking about the Antarctic, the southern?
Yeah, he was asking about the Antarctic.
Oh,
Like
okay,
along
I'm
the
sorry,
coast
I
of
heard the
Yeah.
Arctic. So during this period, that's kind of where the during the summertime, that's we've got the breakdown of the polar vortex. Or during this period, that vortex, or the wintertime vortex is kind of breaking down, and so that's something we know that we're not necessarily capturing just real well. And the observations those observations are at the very edge of it.
I guess I'd say that the fact that it's in all 3, and it's at the very edge, as Maggie was saying, you're reaching darkness. These retrievals require sunlight. I have a feeling it's an artifact in the model.
Yeah, the tropomi retrieval doesn't, and it only gets down that far in the later portion of the experiment, so we might not even be changing it.
Any other questions? Is there, I want to see if Jack Fishman has any questions. Okay, yes. So if there's no more questions, then let's give Maggie another round of applause. And the committee will be convening down in 351. So maybe we can take a bio break and meet down in 351.